Isomers are something that they're two compounds that have the same molecular formula, same number of carbons, same number of hydrogens, but they have different structural formulas, meaning they're attached in different ways. There are three different types of isomers that we're going to look at. The first one we're going to look at are called constitutional or structural isomers. The others we will cover a little bit later. Structural isomers all have the same formula, but they have a different bonding arrangement. Now, don't let the flipping and flopping of the molecules trick you into thinking they're a different structure. Remember, they can be all different ways on the page, flopped around, but the only way to truly tell the difference between a different bonding arrangement is to name the compound, and if you get different names, it's going to be a different bonding arrangement. These isomers have different chemical and physical properties, and definitely different biological properties. So isomers are important to us. Let's look at this first example. We have C4H10 as a molecular formula. 4 carbons. Notice there are 10 hydrogens. That's 2 times 4 plus 2. So this is a straight chain alkane, or just plain alkane, not a ring compound. So I look at this, I can have it all in a straight chain, 1, 2, 3, 4, or I can have it branched. Notice it's 1, 2, 3, 4. This is butane, and this is 2-methylpropane. With 5 carbons, again, this is a regular alkane, not a cyclo compound. I can have 1, 2, 3, 4, 5 in a chain, and that's pentane. This is 2-methylbutane. This is 2,2-dimethylpropane. Different names, same formula, so they're structural isomers. We can throw heteroatoms in there. Notice this compound is different from this one. This is called 2-butanol, and this one's called 2-methyl-1-propanol, and this is diethyl ether. So you can see there's a huge variety of isomers. The bigger the number of atoms in the formula, the more isomers you have. The key thing is identify the formula, identify the name, and if the formula is the same, that must be the same, and the name is different, then they're isomers. Okay, cycloalkanes. We can have alkanes in a ring, and when we put them in a ring, we change the name to cyclo. So you can see 1, 2, 3, so we call it cyclopropane. 1, 2, 3, 4, that's cyclobutane. We see cyclopropanes in the pyrethroid insecticides, and some of the cyclobutanes are used, they're substituted and made highly explosive. C4, the explosive C4, I think, is a cyclobutane. Cycloalkanes and alkanes have different numbers of hydrogens, so they cannot be isomers. For instance, pentane cannot be an isomer, and notice I wrote pentane here. This is cyclopentane and this is pentane. The cyclopentane, I wrote it curved just for the fun of it, to demonstrate to you that it doesn't have to be laid out straight. These two cannot be isomers. Why? Well, even though they both have pentane, this one's cyclo and that one's not. And oops, I have the formula wrong here. That should be C5. This is C5H10, and this should be C5H12. There are 2 more hydrogens here than in the cyclopentane. Notice the ring and write cyclo whenever you go to name the cycloalkanes. Count the number of carbons in the ring. That's your base chain. And then you're going to be using the prefixes that we've learned. So prop, but, pent, hex, oct, non, dec. Then you add ane to the end. You find the substituents and you name them, and then you number their location. And because we're always going for the lowest possible numbers, the number one carbon must have a substituent on it. Only when you are doing the alkyl groups and you have them all on the carbon, sometimes it's hard to say which one of those has to be a substituent. We always give the lower number substituent of two that are arguing for number one position. We'll give it to the one that's lowest in alphabetical order. So here I go to name this, and you can see there's a ring. There's 3, so I call it cyclopropane, and there is a methyl on it. Now, I didn't put a number on this. Why? Well, if I had the methyl here or I had the methyl here, it'd still be 1. So when there's only one substituent, we don't put a number on. But if we have 2 substituents, we do. This is 6 in the ring, so we call it cyclohexane. And then here we have 2 methyls, so we call it 1,1-dimethyl cyclohexane. Those methyls could have been here or here. It doesn't matter where they are. That's where the number 1 carbon is. So go ahead and name this compound. Well, there's 5 carbons in the ring, so it's cyclopentane. We have an ethyl and a methyl, so I put ethyl and methyl. Now I'm going to number this as 1 and this is 2. Why didn't I make this one 1? Because you have to choose the one that is lower in alphabetical order. And you wouldn't go 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5 because you want the lowest set of numbers. And I must go in this direction because that gives the lower set of numbers. Go ahead and try to draw 1-ethyl, 1,4-dimethyl cycloheptane. Okay, to do this, cycloheptane means you have to have 7 carbons in a ring. 1-ethyl, I have to put an ethyl group on. And then on that same number 1 carbon, I have to have a methyl group. On the number 4 carbon, I have to have a methyl group. So it didn't matter which direction I go. I could have gone either way. I could have put it here or here because once I put it in one place, that becomes a number 4 carbon. So 1, 2, 3, 4. There's the second methyl, and we're done. Lipids are organic molecules that do not dissolve in water, but they do dissolve in nonpolar solvents. I've drawn one down here. This is a fatty acid. They have lots of carbons and hydrogens. So you've seen everything except for this looks like a big long alkane. That part is all hydrophobic. That's hydrophilic, but this part's hydrophobic. So the definition that we actually have for lipids are hydrophobic compounds. Because there's so much hydrophobic character here, this hydrophilic character is pretty little. Fatty acids are a type of lipid. I've drawn a fatty acid for you down here. This is a fatty acid. So a fatty acid is a carboxylic acid that has a really long chain. So this is a typical type of fatty acid. They can have shorter chains like this. It's still pretty long, but it's shorter than what I just showed you. This is coconut oil has this fatty acid. Notice there are no double bonds in this. We call double bonds unsaturation, and so since there are no double bonds here, we call it saturated. So this is a saturated fatty acid. Stearic acid is a saturated fatty acid that's found in animals, and it's got a really long chain here. If you look at the fatty acids, the natural fatty acids all have even numbers of carbon. And so here we have 10 carbons, and here we have, I think, 18 carbons. We can have unsaturated fatty acids. Notice there's a double bond in here. When there's a double bond in there you have to take 2 hydrogens away to make that double bond. And so that's not saturated with hydrogen. So if you have all carbon hydrogen single bonds, then it's saturated. If there's a double bond in there, it's unsaturated. This would be called a monounsaturated fatty acid. This right here, you can see there are 3 double bonds in it. Whenever you have more than one double bond, it's called a polyunsaturated fatty acid. There's something called an omega number. An omega number is the number of carbons from the opposite end of the acid to the double bond. So let's look up here to this. 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be called an omega-9 fatty acid. This right here, 1, 2, 3, this is an omega-3 fatty acid. And this is relative importance because they're finding that omega-3 fatty acids reduce inflammation for some reason. And that's an important thing that we need to have done in our body with respect to fats. So here are some more examples of omega numbering. This little symbol right here that looks like a W is an omega. And so if I look at this, this is palmitoleic acid, 1, 2, 3, 4, 5, 6, 7, and omega-7 fatty acid. This, we already did oleic acid, and it's an omega-9. Here we've got linoleic acid, 1, 2, 3, 4, 5, 6, omega. Flaxseed has a polyunsaturated chain, so does canola. What are those? What is the omega number on it? 1, 2, 3. You just count to the nearest double bond. You ignore the additional